Today's lecture is about percent composition, or how can you express how much of an element is present in a particular compound. So let's begin by reviewing something that we know, and that is how we can classify matter according to composition. And the first thing that you have to think is, what about the properties and the composition of that particular substance? Does it change? Can it change? And then you have the division of whether it's a pure substance, like we have here, or if it's a mixture. Remember, a pure substance, constant composition, constant properties. A mixture, you have one or more components there. Each one component individually will have certain properties, but the mixture itself will depend, the properties of that mixture will depend on the composition that you have of those components. Most of these we are already familiar with, and the big point here with this classification is that it allows us to determine composition of matter at the qualitative level. It's just about knowing what's in there so that you can identify it. The purpose of this class is to look at this classification from a more quantitative point of view. Now, it's not only how many things you have in there, but also how much of each component you have there. So to do that, let's focus for now in the simplest substance, which is the element. And in that case, well, there is a single component. So there is no need to express any composition because there is only one component here. So it's going to be always, let's say it's a pure substance, it's always going to be 100% that element. It's not the same story for a compound. The compound is not such a simple substance. There are one or more than two elements there, but you can express how much of each one of those elements you have in that compound based on a fraction or a percentage of that element in that compound. And actually you can do exactly the same thing for mixtures. You can also express the content of each component based on a fraction or a percentage of each component in the mixture. The difference between those two, because they sound like it's the same, but when you're referring to a compound, this fraction, this percentage is constant. And when you refer to a mixture, that fraction or that percentage is variable. That goes along with the concept of constant composition or properties for a mixture or a compound. Okay? So let's jump in the deep of the pool. How do we do this? Okay? Expressing percent composition. What is a percentage to begin with? So percent composition, or percentage in a more general term, is parts per every 100 parts. And those parts here, well, it will have some units, and the units could be anything that you can think of, anything you can measure, anything you can count. It's valid when you count to express a percentage. For our particular purpose of express the percent composition of a compound, we are looking at grams primarily, but we can express that percent composition in actually any unit. You are doing a percentage, you are dividing the same units, you can express that percentage as with any unit. Now the percent composition, when it's referring to those particular compounds, it expresses the mass of each element, and the basis is 100 grams of compound. These are numbers that you can actually determine experimentally, and that's what we call elemental analysis for a particular compound. But we can also calculate it from the chemical formula, and that's mostly how we're gonna do it. Okay, so either you have the mass data for the elements in that particular compound, or you can calculate it from the chemical formula. So if you use the chemical formula, then that percent composition is simply the mass of the element divided by the mass of the compound. Could be from the formula, could be from the experimental data, but it's always going to take that shape. It's the mass of that particular element divided by the mass of the compound, and well, if you're expressing that as a percentage, you multiply by 100. So how about we do that for calcium chloride? And yes, there is another nomenclature checked here. Calcium. What is calcium? Well, calcium is Ca2+. And chloride is Cl-. When you combine these two, you obtain calcium chloride. CaCl2. So if we are doing percent composition based on this formula, then we need to calculate the molar mass for this particular compound. So we have calcium chloride, correct? And that is going to be 40.078, that comes from calcium, plus 2 times 3545, which is the 2 chlorines that you have there, and that number is going to be 110.978. Remember, this is grams per mole. Okay, now this is 40.078. That's the amount of calcium that is in those 110.978 grams of calcium chloride. And this is the amount of chlorine that you have in the mass of chlorine that you have in the same compound. So your percent calcium is going to be equal to 40.078 grams divided by the mass of the compound, 110.978, times 100, that is 36.11%. Now the percent chlorine would be equal to 2 times 3545, because it's 2 chlorines, divided by 110.978, these are grams both, times 100. And that's going to be 63.89%. Now, it's a percentage, and if you add all the percentages for every single atom in that, from every single element in that compound, then everything has to add to 100%. Which means that the percent calcium plus the percent chlorine in calcium chloride has to be equal to 100. Therefore, if you calculate one of the percentages with the mass data, you can calculate the other percentage by just simply say the percent chlorine is going to be equal to 100 minus the percent calcium, that is 100 minus 3611, and guess what? You are obtaining the same number. You have to obtain the same number. So either way, this is this way or that way. It doesn't matter, you're going to obtain the same result. So let's keep that. This is the one that comes next. So how much calcium is present in 250 grams of calcium chloride? Okay, so we already know calcium chloride, correct? And we already calculated the molar mass for calcium chloride, and that was 110.978. And more than that, we already know the percentage of calcium, the percent calcium. I mean, you can calculate it, but because we already did that, let's just use the data that we already have. 36.11%. And well, the question is about calcium, so that's the only number that we need here. These numbers means that you have 36.11 grams of calcium in 100 grams of calcium chloride. And that's exactly what you have here. 250 grams of calcium chloride. We need to know how much calcium you have there. So we simply take 250 grams of calcium chloride and we use that as a conversion factor. And as a conversion factor, you need to cancel grams of calcium chloride, so 100 grams of calcium chloride has to be here at the bottom. And then we have 36.11 grams of calcium on top. Grams of calcium chloride cancel with grams of calcium chloride, and when you complete this calculation, you obtain 90.275 grams of calcium. And that's it. Now let's go back to this one. This question asks you how many pounds of carbon, hydrogen, and oxygen you have in a 5-pound bag of sugar, and this is the formula for sugar. Well, these are pounds. That doesn't mean that you need to do any conversion at this point with the pounds, because what about we just focus on calculating the percentages here? So we need the molar mass for sugar, right? So if sugar is C12H22O11, then the molar mass would be 12 times 12.011 plus 22 times 1008 plus 11 times 15.999. That would be equal to 342,297 grams per mole. Therefore, your percent carbon is going to be this number, 12 times 12.011, divided by this number, 342,297. These are grams, times 100, and that is 42.11% carbon. Then we do the same for hydrogen. Hydrogen would be 22 times 1008 grams divided by 342,297 grams times 100, and that is 648%. And at this point we have the option of, if we are doing oxygen, we can simply say percent oxygen is going to be 100 minus 42% from carbon minus 648% hydrogen, and that is going to be equal to 51.41%. Okay, so now this is not the question. Okay, these are the percentages, but the question is how many pounds of carbon you have in there. So for example, this is a percentage, right? And we calculate this percentage in a basis of grams, but this percentage also tells you that there are 42.11 pounds of carbon in 100 pounds of sugar. So that is the power of the percentage. It allows you to instantly convert between units. So that is a nice thing to have. So carbon in that bag would be equal to, you have 5 pounds of sugar times, we use this as a conversion factor, we have 42.11 pounds of carbon per 100 pounds of sugar, so these pounds cancel with these pounds, and that gives you 211 pounds of carbon in that bag. We do exactly the same thing with hydrogen. So hydrogen would be equal to 5 pounds times 648 pounds of hydrogen per 100 pounds of sugar, and that is 0.33 pounds of hydrogen. Now if you want to find out how much oxygen you have, we can take also the shortcut, because 5 pounds is equal to carbon plus hydrogen plus oxygen. Therefore oxygen is going to be those 5 pounds minus 211 pounds coming from carbon minus 0.33 pounds. This is carbon, this is hydrogen. So oxygen is 2.56 grams. Oh, sorry, it's not grams, it's pounds. Okay, you have 2.56 pounds of oxygen in that bag. So this is how you can go from percent composition to mass composition in that particular bag. Okay. Another type of problem that we can solve is kind of going back in the reverse direction from the 250 grams of calcium. So now how about we have 100 grams of carbon and you convert all that to CO2? How many grams of CO2 would you form? Basic for every single type of these problems, you need to calculate the molar mass, which is 2.011 grams of carbon plus 2 times 15.999 from oxygen, and that is 44.009 grams of CO2, grams per mole of CO2. The thing is this is the amount of carbon that is contained in this amount of CO2. So we can write that as a conversion factor. 12.011 grams of carbon equals 44.009 grams of CO2. And this is your conversion factor. And all these, when you work with this percent composition, they are very, very useful conversion factors. So we have 100 grams of carbon. And we know that every 44.009 grams of CO2 contain 12.011 grams of carbon. These cancel together, and you finish this calculation. When you complete this, you obtain 366.4 grams of CO2. Therefore, you obtain 366.4 grams of CO2 out of 100 grams of carbon. So these are the types of problems that you can solve by using percent composition. You don't always have to go to percent composition. If you establish what the mass relationship is between the elements and the mass of compound, you are good to go. Okay, you can calculate anything that comes to mind when it comes to those relationships. Okay.